Okay, so just to kind of like recap where we finished off at the end of last lecture. So we were going over this factorisation of basically taking quadratic equations and seeing if we could solve those using this kind of general formula where we've got one x and another x in a bracket, and we multiply those two brackets together, we get something that looks like this equation, okay, which is generic, a kind of a generic form of a quadratic equation. And then to solve quadratic equations, we basically do the process in reverse. We can basically try and think up numbers for m or n that basically work and produce two basically halves of the thing that's times by each other to give you your quadratic equation. Okay, this is just to whiz through. You could have solved those if you chose to for homework. But then we have this term called this kind of like this special case of a perfect square. It's kind of when we finished off, where what this basically means is when we work out what the numbers are that go in here, okay, the thing on either side of those two brackets are the same. Okay, so in this case it would be x and x minus 5, and it would be x minus 5 on either side of that bracket. Okay, so that's why it's called a perfect square, and this is important, and we'll come on to why it's important in some of Masco's lectures, because this basically allows us to solve any quadratic equation, even one that doesn't end up having nice whole numbers. Okay, so Massimo will go through that with you and where. Okay, so there are just more examples here which you can work through. This is slightly more complex in that basically rather than just having just an x at the beginning, we have 2x. Okay, so we need to think about that when we're basically trying to come up with answers. So in this case, we know that the first term can be factorised into either x and 2x or 2x and x. So these numbers are like that. So when we then trying to find numbers of m and n that work for the third term and the middle term, we need to think about that we're going to be multiplying one of those by 2. Okay, so that's the example of that. So just more examples in terms of, so here we've got, we'll just go through this. So we've got 3x squared plus 17x plus 10. Okay, so this time we're looking for things that go into our brackets. There's going to be an x here and an x here, right? And we don't know what's in front of them, except the thing that goes in front of them has to be basically a factor of this. Okay, and in this case it's relatively straightforward. It's either 3 or 1. Those are the only factors of those numbers. So 1 and 3. Okay, and then when we come to work out these numbers here, this one, our numbers here, we call this m and n. Okay, the numbers that are going to go into that space there. Okay, so we know that when you multiply them together, okay, we have to equal 10. Okay, but when we add them together, we're not going to equal 17, because when we add them together, we're going to have to times one of them by 3 and the other one by 1, and then add them together. Okay, so if it just takes a little bit more thought in terms of, well, what are factors of 10? Okay, so those could be 1 times 10 is 10. So we could have 1 on 10. We could try and figure this out. So could we times, say, 1 by 3? You get 3 and 1 and 10 times 1. We couldn't really add those numbers together to get 17. Okay, so we could try and think of another factor of 10. So 2 times 5 equals 10. Okay, then we look at, if we times 2 by 3, we get 6x. 5 times 1, we would get 5. So 6 and 1, we can't add those together to get 17. But if we do it the other way around, 5 times 3 is 15. 2 times 1 is 2. So we put 2 and 5 in there. Okay, and we know that they're all pluses because these are all pluses. Okay. So having the thing in front of the z squared or the x squared, I should have written z squared, but I guess you get that picture. Deliberate mistake and all that. It makes it just a little bit more tricky. Okay, so the answers are there. Got the right answer. That's pretty good. Similarly, I mean, this is just a slightly more complex example, and this is just, you simplify that. So the first thing you have to do is basically factorise the bottom thing here. Okay, I'm going to let you can do that in your own time first. Okay, first term could be divided by 2, and the factors at the end are 3 and 3, 3 and 3, 9 and 1, and you can work out that it's not going to be 3 and 3, but it's a 9 and a 1. So 2 times 9. 18 minus 1 times 2 is you man there. Anyway, okay, so that was just basically factorising quadratic equations, and there'll be more examples of that in Massimo stuff, and there's also examples that I posted on I think this week's Learn on the Khan Academy. So do go through those kind of when you can. So the rest of today's lecture is going to be about rearranging equations. So rather than just factorising them, okay, we want to basically manipulate them and move them around so we can find the thing we want. And it's just kind of, it is the first level kind of like super straightforward. The only examples we're going to do today are super straightforward, but this can get kind of sometimes a little bit counterintuitive and tricky to do. So another word for rearranging is transposing. I don't know why there are 2 words for it, but you know, that's English for you. Okay, so all we're doing is basically having some kind of really simple equation like this. So this is the equation for the area of a circle, and if we wanted to find out, in this case, A is the subject of that equation, so A equals some kind of horrible mathematical thing, we might want to rearrange that to find R. And basically, this is basically the golden rule. Okay, so everything you do to one side of the equation, okay, you must do to the other side of the equation. Okay, and as long as you stick to that rule, okay, even if you do the wrong thing, okay, so you could start off trying to rearrange this equation by adding 412 to each side. Okay, that's totally irrational and a silly thing to do, but it would still be correct. Okay, the equation would still work if you just added 472 to both sides of that equation. Okay, as long as you do it to both sides, it doesn't matter. Okay, so in this case, I'm going to just whiz through this example super quick, but you know, what if we wanted to know what R was? So we wanted an equation where we could work out the radius of a circle of known area. So the first thing you might want to do is you might want to remove pi from the right-hand side of the equation. So you just divide both sides of the equation by pi. So in that case you have A equals pi r squared. You divide both sides of the equation by pi. Okay, just done the same thing with both sides of the equation. And that gives me A over pi, but it also gives me a pi over pi. Okay, so I can cancel those both out. Okay, so cancelling you don't have to do to both. You can't cancel one thing to both sides of the equation. Okay. And in this case we've got r squared. If we wanted to turn that into r, we would make the square root of both sides. Okay, and that is the same as saying r squared of a half. Okay, so raising things to the power of half is the same as square rooting them. Okay, and you know when you've got exponents, okay, an exponent of an exponent, you times them together. So a half times 2 is 1, so that is equal to r to the power 1, which is equal to just r. So now we have an equation where square root of a over pi is equal to r. So we could then, if we wanted to use that equation, we could just plug our numbers into that. So we've made r the subject of that equation. Those are, yeah, that's what it says. Okay, so we could quickly go through some examples of this. Let's pick, I don't know, let's pick this one here. So if I just open up a thing in our, just a word answer, so yes. Okay, so another example of rearranging equation. I put this in just because, you know, I thought I'd tell you a little bit about me. What we're going to do is we're going to work out how high it is possible to pole vault. Okay, so a couple of years ago, the pole vault world record was recently set by this guy, Raymond or Reynard Levine, up here, 6 meters 21, I think, something like that. Okay, women's world record is here, and my personal best is here at 4 meters 32. So I would have had the world record in 1920, but I'm not that old. Anyway, so one question you can ask is, I mean, can this carry on increasing forever, or is there some limit to how the world record will proceed? Okay, so how high can a human vault? Oh, I put these in. Oh, put them right in the face. Some quite good ones here. This one's particularly amusing. Bit of a and it's really hilarious. And this one is the most painful. All looking really good, and then anyway, you'll remember this. So here's our model that we're going to basically create mathematically to work out how high it's possible to pole vault. So our pole vaulter runs in as fast as they can. So they have some kinetic energy. Okay. So their kinetic energy can be described as 1/2 times their mass times their velocity squared, half mv squared. You might remember that from physics. Okay, they jump. Okay, so there's some energy in their jump, which we'll ignore, and then they convert all of this energy into height. Okay, so the amount of energy that they have at the top of their pole vault is essentially just their gravitational potential energy. Okay, so the kinetic energy can be described as 1/2 mv squared. Okay, and when they get to the top of their pole vaultness, their energy is the mass times gravity times height. Okay, you might have done this before at school. Potential energy is mgh. Okay, so our model is going to just basically, all it's going to do is say that you convert all of your kinetic energy into potential energy. So the whole system, kinetic energy equals potential energy, which is this equation here. Okay, 1/2 mv squared equals mgh. Okay, that is the model for as high as anybody can pole vault. Okay, so all we need to do now is rearrange that equation. Okay, so very simply, all we're going to do is we want to make h the subject of that equation. Okay, so we could divide both sides of the equations by mass and gravity. Bring those over to this side here. Okay, and then the mass then cancels out. So we've got mass divided by mass. It doesn't matter how heavy you are, it doesn't determine how high you can pole vault, which is good. Okay, so we end up with an equation like this. And then we can plug some numbers into that. So we know what gravity is. That's 9.81 meters per second squared. Okay, which you will remember from the first tutorial, I think, maybe? Maybe not. Yeah, you did that in the first tutorial, right? It's like question 14 or 13. It's definitely in there, yeah? And V, our man here, Usain, okay, so he can run, when he gets like his fastest, when he was running the 200 meters, 44.72 kilometers an hour, which is pretty fast, okay? So all we need to do now is plug those equations into numbers. Plug those numbers into that equation, okay? But bear in mind that what we should always do is we should always convert stuff into standard units, or at least the units that we're interested in getting our answer in. So convert velocity into meters per second, into meters per second. So you need to times it by 1,000 to get kilometers into meters, and then divide by the number of seconds there are in an hour, which is 3,600. Okay? So our Usain here can run at 12.42 meters per second, which is still pretty fast. So, yeah, so we can then plug those numbers into the height, okay? And you can do that in your own time. And notice that I'm now quoting the answer, okay, to the lowest number of significant figures that I was given information, okay, which in this case was gravity. Okay, so 7.86 meters. So 7.86 meters is the highest increase in potential energy that you get while pole vaulting. Okay? But you don't start off at the ground because your centre of mass is not on the ground while you're running, so a bit of height there. So it turns out that Usain Bolt, if he decided to take up pole vaulting, would be able to pole vault approximately 9 metres high. Okay? So that's what the model suggests. When we compare that to the actual world record, which is 6.2 metres, that's a lot more. Okay? So we can then go back, do that kind of like that scientific method that we did in the first couple of lectures. We go back and say, look at our model, and say, is our model realistic? Okay? So there are a whole bunch of reasons why our model might not be realistic in this case. So the speed that Usain Bolt runs, holding an enormous pole, is probably not as fast as he can run when he's not holding it, so his velocity is probably a bit less. And also maybe some of this energy transformation from kinetic energy to potential energy, maybe that's not 100% efficient. So we might go back and revise our model, okay, with some different data and some different assumptions. Anyway, so that was kind of that. So that's just a really simple example of just rearranging equations, and I recommend that you go through some of those examples in the PowerPoint and just see if you can rearrange those equations kind of to find the subject that's of interest. Okay, so moving on now to word problems. So this is, once again, I think I said this at the beginning of the course, but this is the hardest part of this maths course. It's not learning the maths or kind of learning what quadratic equations are or how to solve them or learning the calculus. It's going from some question or some science or a list of statements about the way that the Earth works, or in this case we'll go through a really, really straightforward simple example. It's about going from that and working out what the maths are that you have to do. Okay, it's about figuring out what equations you should be trying to make and what you should be then doing with those equations. Okay, so so some tips and or tricks. So we'll just read the problem. Read the problem and then basically trying to figure out what you're being asked. Okay, so what information is it giving you? What result is it asking for? And you can, once you've figured out what it's asking you, substitute those words for variables that you can then plug into equations that you create. And it's basically, this is the hard step. Find the formula. Or formulae. I think it's just formula. Anyway, whatever. And once you've found the formula, then the maths should be fairly straightforward. Oh, and always check your answer. Okay, so in the case of that Usain Bolt one, you think about it. If you came up with an answer that was 900 meters instead of 9 meters, you'd go, well, I've definitely made a mistake there. Okay. Or if you came up with an answer that was, 2 meters, you're like, well, no, that's definitely wrong. Okay? Does your answer sound reasonable? If it's not, go back and check your unit conversions, go check your equations, that sort of thing. Okay. No, I don't think we'll do this example. Okay, we'll do this example. So this is just some words, okay, here. The area of a rectangle is 6 meters squared. The perimeter is 10 meters, okay? What are the length and the size, okay? So in this case, we're just given some words, okay? And we can think about just from those, what can we do to create equations, okay? So we know that the area equals 6, okay? And the length of the sides are what we want to get, okay? Okay, and we've got 2 types of length sides, right? Okay, so we'll call L equals length and W equals the width. Okay? Yep. So we could say that 2 times L plus W equals 10. Yeah? And we also know, okay, that the area is going to be L times W equals 6. Yeah? Happy campers? So now what we've done is we've got the things, we've taken our information that we were given in the question and we've basically substituted in, we found variables that we want to find the answer to, we've given those little algebra jobbies here, and we've written down two equations, this guy here and this guy here, and then what we need to do now is then do some maths to solve this problem. Okay? And the maths that we're going to have to do here is we're going to have to solve simultaneous equations. So we've got two equations, okay, and we have two things that we don't know. Okay, so if you've got two equations and two unknowns, that suggests that you can solve those equations. Okay, so one way of doing this is by substituting in, okay, for basically rearranging one of these, and the bottom one looks like it's the easiest one to rearrange. Okay, so we could rearrange that to say W equals, if we divide both sides of that equation by L, W divided by W divided by L equals 6 divided by L. Okay, so those cancel out. You guys see that? Was that? See it? Not see it? Give it a go, eh? So now we've got an equation for W. Okay, it's not giving us the answer, but we can then substitute this up into here. Yep. Okay, so that would then give us 2 times L plus 6 divided by L. Yep. Okay. We could then try and basically rearrange this equation to find what L is. Okay, and in that case, we could divide both sides by 2. So we get L plus 6 over L equals, what does that equal? 5. Yeah. So this can be rewritten. How can we do this? L plus L to the minus 1 times 6 equals 5. Yeah. Now, what we need to do now is basically try and find a common factor of that. I should have gone through this. How do I? So that would be is that right? No, that's not right. I'm all horribly lost here. There is a way of solving this equation, honestly. Times it by L. Yeah, I think that's the way to do it. Yeah? Yeah. Yeah, so if you times everything by L, you would get, well, let's go back to our L plus 6. If we times everything by L, then we would get L times L plus 6 over L times L plus equals 5 times L. Yeah?
Should the 5 not be a 10 then, since you're not trading over 2?
I've already done a mistake here, but yeah, well spotted. But yeah. Right. And then that can be simply written L squared plus 6 equals 5L. Okay, you can then rewrite that L squared minus 5L, so I get minus 5L for both sides, plus 6 equals 0, and then you've got this quadratic equation. Okay? So we can look at that quadratic equation and think, well, can we solve that by factoring? Okay, in this case we can draw our two brackets, okay? And we know that because we've got 1 here, our first term in both brackets is going to be L. And we need a number, 2 numbers, m and n, that are going to be, when you times them together, you get 6. And when you add them together, you get minus 5.
Would it be L minus 5 and L minus 1?
So, because we want a minus here, yeah, and we've got a plus here, when we times them together, okay, they're going to be positive. Okay, so we know that the signs are going to be the same. But when we add them together, okay, it's going to be negative. So that tells us they're going to be a negative. So we can put in the symbols first, yeah? And then we think about 2 numbers that we can add together to get minus 5. Okay, so that's either going to be 1 and 5, or 1 and 4, or 2 and 3. And you've got to times them together to get 6. So that means it has to be 2 and 3. Okay, 2 and 3. Okay, so that means that, and that is equal to 0. So that means that our answer is either going to be L equals plus 2 or L equals plus 3. Yeah? So now we've solved for one of the variables. Okay, we can go back to our any of our other equations here. Okay, length is width times 6, or length times width equals 6. So we could plug either of those into here. So W is equal to 6 over L, and W is equal to 6 over L, which is equal to 6 over 2, or 6 over 3, which is 3 or 2. Okay? So what we've done there is we've basically plugged in our answer back up into our equation at the beginning, okay, to check that we get the right answer. Okay? And we can do that quite easily now. We've got 2 and 3. Okay, so if we times those together, we do get the area, which is 6. And if we use this equation up here, so 2 times, or basically, 2 plus 3 is 5, times 2 is 10. So checking this equation up here then gives us the right answer. Okay, so we can do one of those steps. So, yeah, so just to go through, yeah. So solving these simultaneous equations is what we've just done. So the key thing is that you find the equations from the words, okay, and then you rearrange one of the equations, okay, that gives you the value one of the values you're looking for, and then substitute that into the other equation, okay. Rearrange that equation, okay, and in this case that was a bit tedious for me, but most of you kind of like spotting my mistakes. Good, excellent. And then once you've figured out what that variable is, sometimes you have to do quadratic equations, sometimes you don't. Okay, once you've figured that, then you can plug those numbers back in to the equations that you first thought of, and that gives you both of your answers, and then you can check that those answers are correct by using the other equation to check it out. Okay, so that was basically rearranging equations and word problems. So just that, I mean, that's the approach to word problems. We'll come across more and more examples as we go through the course, okay? But just to point out that that's the kind of that is the hard part. So this next part is solving linear equations. So linear equations are unlike quadratic equations in that they only have basically x to the power of 1. So they don't have x squared or L squared or anything like that. They just have this one y equals x times something and then plus something. These things, a and b, are constants. Okay, so these types of equations, if we were to plot them on a graph, okay, of x and y, okay, if we were to plot these on a graph, we would always get straight lines. Yeah, it doesn't matter what orientation they are, where they go on the graph, but that type of equation where A and B are any number, you will always get a straight line. Okay? And these basically constants A and B, so they're not always called A and B, sometimes they're called M, sometimes they're called C, sometimes they're called, they're just any algebraic variable in that position in the equation. They relate to where these lines on the graph are. Okay, so A is the gradient of the line. Okay, so that's basically the slope. So if you measured that distance and that distance, okay, so we call this distance the change in y, delta y, okay, and this is the change in x, big delta x. That's just how, for any bit on the line, how far you have to go across to go up any unit, okay. So in this equation, y equals ax plus c. This term here is delta y divided by delta x. Okay? So if that was for this line, okay, and I drew another line that was like that, okay, it's a steeper gradient, okay, so this variable a would be a bigger number. Okay? X is the independent variable, so that's the thing that can vary, and b, dependent variable, will it say b? Yes, b at bottom. B is the value that line, any line, intersects the y-axis. Okay? So you can see how that works in the terms that if you make, in this equation, if you make x equals 0, okay? If you make x equals 0, this term here, a times 0, will always be 0. Doesn't matter what value of a you have. So that's basically the value of y when x is 0. And that's that point on there. Okay, so now we've basically described these linear equations. How do we go about actually solving them? And what kind of information do you need to solve them? So imagine that this thing here is the this graph I've drawn on the board. So in this quadrant up here, which is this quadrant, and this is basically where most of you kind of think of kind of mathematical number space where both y and x are positive. Okay, but the other three quadrants do exist where you have negative values of y, negative values of x, yeah, and negative values of both. And that's what these things mean here. So where x is greater than 0, but y is less than 0, so that means y is negative, x is positive. Okay, so if you think about how, if you wanted to define where any line was in space, okay, if you knew it was a straight line, okay, you only need to know 2 points on that line, and that tells you everything you need to know about that line. Okay, so if I have a point here, a point up here, okay, like it shows on the graph, there is only one way to draw a straight line between those points. Okay, so if we know where those 2 points are, we should be able to work out what the equation of that line is. Okay, because there's no way that it can be any other line, so we should be able to work that out. Okay. Okay, so we should be able to work out the slope, because if we know what this point is here, so if we know, for instance, this point here can be described as a number across here, say maybe 1 across and maybe 2 up. Okay, so that's one of the ways that we write down the position of points. Okay, we just open brackets 1, comma 2. That's basically x is 1, y is 2. And then up here we could say x is, let's say x is 5, and y is, let's say, 4. Okay? So we know that it's a straight line. Okay? So we can say y equals mx. Okay, so a small change in that. Yeah, like I said before. So we can work out, if we know that what we're looking for is an equation that's y equals mx plus c for ax plus c. Okay? Y B, doesn't really matter what these are, but we need that term, we need that value, okay? But that's the equation for a straight line, so that's what our first kind of assumption that we're making. So with just these data here, we can work out what the gradient is, okay? Because we know how far across we are and how far up we are, okay? So delta x is 5 minus 1, okay? And delta y is 4 minus 2. Delta y is 4 minus 2, so that's 2. Okay? Now you see on this one, I minus what was in this one by this one. Okay? Yeah? And then I worked out the gradient, so A or M, whatever, is equal to 2 divided by 4. Yeah? So a half. Now, it doesn't matter which way round you do this, working out what the difference is, as long as you do it the same for both of them. Okay? So I could have done 1 minus 5, which is minus 4, and I could have done 2 minus 4, which is minus 2, and that is still equal to plus a half. Okay? So it doesn't matter which way around you do it, as long as you do it the same for both. You can't do 1 minus 4 and 4 minus 2. Yeah? Happy campers. Okay, so this gives us our gradient. So we now know that y is equal to 0.5 x plus b, or whatever we're calling this variable that's the thing at the end, the intercept with y-axis. So we can rearrange this equation, okay, to make b the subject, okay? So that would be b is equal to, and we're going to take y divided by 0.5, no, you idiot, y minus 0.5x. Okay? So all I've done is rearrange that. Now, what we need to do is we need to plug in some numbers where we know y and we know x. Okay? So that's basically any point along this line, okay, where we know both y and we know both x. Okay? And we actually have two places where we know that, here and here. Okay, so we could plug in our first one here, so we know that b is equal to our y value, which is 2, minus 0.5 times our x, which is 1. Okay, so this is simplified to 2 minus 0.5 equal to 1.5. Okay, and we can look at our graphical drawing of this and say, does that look right? Okay, is the intercept of this graph approximately 1.5? Okay, so that's 2, that's 0. Is that approximately 1.5? Yeah, so it looks like just by sketching out we get the right answer. We could check our answer again by putting the values that we know for the equation now. We know we've got y equals 0.5 x plus 1.5. Okay, we could put our value for x for this other point in up here. Okay, so we could 0.5 times x, which is 5, so that would be 2.5 plus 1.5. Okay, so 2.5 plus 1.5 is 4, and that gives us our value here. So we've used the other piece of information just to check our answer. Okay, so this is kind of what we can do with, this is basically how we go about solving linear equations. So if you've got, you know it's a straight line, okay, and you have 2 points on that line, you can work out the equation of the line. Okay, so bear in mind if you find a word question that's giving you kind of like points in parameter space, okay, maybe speed and time or something like that, so then asking you to work out what the equation is, then you can do it this way. Okay, so this goes through what I've just done that. Okay, so yeah, always verify it by doing the switcheroo back into the. Okay. So just to kind of like recap, if you've got slopes that are negative like that, that means that your parameter in front of the x will be negative. So I guess that's probably something like -2, -1, -0.5 for those three slopes there. If you've got a horizontal line, okay, so that means that this parameter here is 0. Okay, so it doesn't matter what the value of x is; it will always be the same. Y will always be the same value. So in that case, the parameter, the gradient would be 0, or you can have a positive gradient. And likewise, you can kind of, just by looking at the graphs, you can say, you know, what the parameter c would be. So that's some examples which you can work through, which I'm not going to go through now, but you know, do go through those in your own time to think if you can, like, figure them out. Now, I've just got these examples up here because this is basically another kind of type of way of solving equations where you might be given a word problem that gives you two linear relationships. Okay, so this could be something like one of these kind of speed equals distance divided by time thingies, where you get two people that are running at different speeds. Do they kind of like intersect with each other, or something like that? But basically, these give you, if you draw these two equations, okay, or rearrange them to be y equals mx plus something, okay, you can see that in both cases, in all three of these cases, yeah, they're linear equations, because none of the y's or the x's are raised to the power 2 or anything, they're all power to the power 1. So that means that they will be straight lines. Okay? And if you have two straight lines, okay, that are not the same equation or don't have the same slope, okay, so if you end up with the same slope, they'll be kind of parallel lines. Yeah? So if we were to rearrange the top one, we would have 3x or minus 3x so we'd have 3x minus 5 equals 2y, and then you divide everything by 2. So the gradient would be 3 divided by 2. And on the one on the bottom, the gradient would be something like 4 divided by 2. So the gradient would be 2. Okay, so they've got different gradients, those two lines. They would intersect. So at some point, the two lines would meet. Yeah? So that means that you should, okay, be able to figure out, if you know the equation of this line and you know the equation of this line, you should be able to find that point. Okay, you have all of the information to find that point. Okay, so all you have to do is rearrange one equation to be y equals something, okay, and the other equation to be x equals something, yeah, and then substitute that x equals something into the first equation, okay. So then you only have an equation which is y equals something y. So there's only y's in the equation. Okay? You should then be able to rearrange that equation to get y equals something, okay, without any other y's in it. And then you should be able to solve that equation, find an answer for y, and then plug that value for y into either of the equations that you've created and figure out what x is. And that will give you the y and the x variable for that point there. So that's, we could, yeah, I guess let's just go through that first example. We're being watched. So, yeah, let's just do that. So, we won't top hat it, we'll just go through it. So we've got 3x plus 2y equals 5 and 4x plus 2y equals 9. Okay? So we rearrange the first one.
Is it not minus?
Oh, where's the minus?
Minus 2y.
Oh, you fucking legends. Right, excellent. Do we even have a pen that works? No. How many? So rearrange the first one. Okay, so we would add 2y to both sides, 3x, and minus 5 to both sides equals 2y. Okay, and then just put that 5, 1, 2, bottom there. And then this one we want to rearrange to get x. So 4x equals 9 minus 2y over. Okay, so two equations there. We can then plug either one into the other one. Yeah? So let's see if we can actually do that. So let's do the top one. So we're going to put that into there. Okay, so 3 times 9 minus 2y over 4. Okay, minus 5 divided by 2. And that is equal to y. Try and simplify this a little bit. So this term here, I guess we could start to simplify that, saying we've basically got this. This is 9 divided by 4 times 3 minus 2 divided by 4 times 3y. Yeah, so that's that bit there. Minus 5 divided by 2. This simplifies a little bit more. So 9 times 3 divided by 4, so that's some horrible number. I believe that's this. This bit here is 6 fourths y minus 5, this is 9, 4, 3, all over 2. Okay, so we need to basically rearrange this to find just one y, and we can do that somehow. How do we do that? I swear I did this earlier, it was really straightforward. Times 5. Oh. Anyway, this is home time now. Oh man. There definitely is a way of doing this that is totally straightforward and is eluding me. Divide both sides by y, makes sense. Yeah, let's try that. If we divide both sides by y, that would be 1. That would be y there. And then we've got 9, 4 times 3 divided by y divided by 2y minus 6. 4y divided by 2y, y's cancelled, minus 5. And then you see all of these terms, these two terms can be grouped. That's equal to 1. So we could rewrite that 9, 4, 3 divided by 2y minus 5 divided by y equals, we add that to both sides, so 6 over 4 over 2, which is the same as saying 6 over 8. So this here, we can basically rewrite that as 1 divided by y, open the bracket, and then 9 over 4 times 3 divided by 2 minus 5. Okay? And that equals 6 over 8. So what I've done there is I've rearranged it to basically turn this equation that had 2 y's in it, was really annoying and confusing, into an equation here that now only has 1 y in it. Okay? And it has this thing in a bracket. So I can then, so this is where kind of finding a common factor can help you by taking an equation that's got 2 of the things that you want to know, and then get rid of those, and so you only have 1. This can then be rearranged, so y times both sides by y now, so this becomes y times 6 over 8 is equal to 9 over 4 times 3 divided by 2, which is, that's 5. Okay, and then you could then y equals 8 over 6, and then all of that. Okay, so I'm not going to go through and actually work out what that is, but once you've done the rearranging, you can put the numbers into a calculator. You can get what y is then, okay, and then plug that in and find out what x is, hopefully. There's the answer. Okay, so have a go at doing those, okay, if you, yeah, so I mean, the answers are in the PowerPoint there, so you should be able to go through and rearrange these equations and solve them and get those answers, okay. It can be a bit of a mess, like that was, okay. Hopefully you can see the steps of what I've done, okay, so I started with my 2 equations, I rearranged them to make the subject of the equations y and x, okay, make the subject of those equations y and x. I then substituted in x into this equation, so I then only have one equation that has one of the variables in this case it has multiple times. And to get rid of that multiple times the variable, I basically found a way of rearranging it, okay, until I could get something that is got the same variable in, raised to the same power, so y to the minus 1, y to the minus 1, which means you can then kind of extract that out as a common factor, okay? And that basically means that you can convert 2 variables into the 2 versions of, or 2 appearances of the same variable into 1, okay? Once you've done that, you then rearrange the equation again to make that the subject of your new rearranged equation, which will give you the value of it, which you can then plug into these equations to get the right answer, hopefully. So have a go at that. Enjoy Massimo tomorrow. Yeah, bring questions to the tutorials or the office hours if you're struggling.